Okay, so the topic for today is, the topic of this chapter is methods for three-dimensional data acquisition, okay? And so this is becoming definitely a big issue for visual effects. Not only are you dealing with, 2D images that come off of your cameras, but it's also very important to acquire three-dimensional information about the sets and the actors and the props as you're filming a movie set. Those things help to create the visual effects after the fact. And so what I want to talk about this morning are basically different ways of acquiring 3D data with basically laser ranging. Okay, so there are several ways you can get 3D data, and we're going to talk about those in the first 3 lectures of this chapter. The first one, like I'm talking about today, is called LiDAR. LiDAR, and also we'll talk about time of flight sensing. The second one is called structured light scanning, and the third one is called multi-view stereo. And so those are going to be the topics of the next 3 lectures. And then the fourth lecture is going to be basically about computer vision algorithms for manipulating and processing this data once you have it. Okay. So for the most part, we're going to be mostly talking about just acquisition in the first couple lectures. And so here's an example of what I'm talking about. This is what's called a LiDAR sensor. LiDAR stands for well, actually, there's some debate about whether it actually is an acronym or not, but the idea is it's an analogy to radar. LiDAR stands for light detection and ranging. And so the idea is that this device, which we have on campus, you can see this is in Troy, New York, sits on a tripod. This slowly spins around, and what's happening is that laser pulses are going to come out of this window and hit objects in the scene. And usually the way that these sensors work is that they measure the time it took for the laser pulse to bounce off an object in the scene and come back, and that time is used to calculate the distance to objects. We'll talk about exactly how that works in just a second. And so this is a pulse-based LiDAR scanner. I can already tell that my computer is a little bit laggy, so let's see whether it's going to keep up with me writing here. No, it's not bad. Okay, so today's topic is basically LiDAR and time of flight scanning. Okay. And so one way to think about LiDAR is it's kind of like the laser measuring tape that you get at Home Depot, right? So you have this little device, you point it at the wall, a laser spot goes out, and you aim where you're looking to measure the distance to, and it comes back and tells you immediately how far away that surface is, right? And so the advantage of such a system, instead of using like cameras to infer the distance between objects, and that's kind of what we're going to talk about next week, is that you are using a kind of a physical, real-world measurement to directly acquire the distance of something. Like you're directly probing the distance. And so, in some sense, this is kind of like the gold standard for measuring how far away stuff is. You can do it with cameras alone using things like structure for motion and multi-view stereo. We'll talk about that next week. But, when you're talking about really doing accurate 3D scanning, you're going to use some type of laser scanner or structured light scanner. So we'll talk about those technologies right now. And so what you get at the end of the day is kind of like what you'd call a depth or a distance image. And so basically you have a sensor. I'm going to draw this kind of poorly, I'm sure. So this is a sensor. It probes the scene. You've got some object in the scene. And then that pulse comes back to the sensor. And what you get basically is, depending on the angle of this pulse, you kind of get this distance map as a function of theta and phi, where these are the 2 angles that the sensor can beam out its laser rays. Okay, and so this can be interpreted as what you'd call a depth image or a range image. And then if you do the conversion from spherical coordinates to Cartesian coordinates, basically here you have a theta, a phi, and then you have the distance itself, which is like the radius with respect to the scanner. Then you can convert that back into absolute values of x, y, z to get a 3D position of something. Okay, so like I showed you, this is an example of one such laser scanner. And then this is another kind of laser scanner. So I'm going to talk about in a second the distinction. Some of these scanners are what you call pulse-based, and some of them are called phase-based. We'll talk about what that means on paper in just a second. You're also probably familiar with like the DARPA Grand Challenge, self-driving cars, also like the Google cars, also have laser scanners on them that operate on the same principles. This is a Velodyne scanner. Basically, here there's this laser scanner on the top of this car that is spinning around very rapidly and acquiring 3D points. Okay, and so in the interest of trying to not have my computer slowed so much, let me just kind of show you the type of data that comes off of the scanner. And so this is a scan of the building of the VCC on campus, right? And so this was acquired by one of my students many years ago. And so what you're seeing here, if I can remember how to manipulate it, is you can see that the quality of the scan is pretty good. You can kind of make out the individual textures of patterns of bricks and stuff like that. This is kind of a settable parameter. You can decide how finely you want to scan the surface of the building. Of course, it may take you a long, long time to scan the building if you say, I want to scan the surface every 5 millimeters, something like that. And you can see that if I turn this from surface to points, that really the surface is made up of basically these columns of points, each of which has been probed independently by the scanner. And so, one time I heard LiDAR point clouds being described as, a swarm of angry bees, right? Because if you really start to look at the data that you get back from the scanner, it's not this beautiful surface mesh, although you can connect up triangles into a nice looking mesh later on. But really all you have to work with are these 3D points. And so sometimes it's tricky to understand, how do I know how to connect these points up into a reliable mesh? Because if I go back to my mesh, you can see that, well, actually, maybe let me see if I can go with a wireframe. That may be a little better. Right, so here you can see the points have been kind of connected up into meshes. And of course, there's a big question about, how do you decide which points should be connected into a triangle and which points are too far away to be connected into a triangle, right? So we'll draw some sketches in just a second. Of course, you could say, okay, well, if the length of a triangle edge is too long, well, then obviously I shouldn't connect it up into something. But that's kind of hard to distinguish sometimes because of the ways in which the laser rays kind of graze the surface. I mean, you could probably argue like these triangles here probably shouldn't be here. But this is a scan that is pretty high resolution. I mean, you can make out all sorts of cool details. One thing that's definitely characteristic of laser scanning, which you can see in this view, is that you're only scanning the surface from a fixed perspective, right? And so if you fire a laser ray in one direction and you hit something, then you don't see anything that was behind that laser ray from that perspective of the camera. And so you can see, for example, that this tree here, because the laser is way over here, we hit all these things in the tree, and then that creates this kind of tree shadow on the surface of the building, and we never actually directly probed those intensities. To get those, we would have to move the scanner over to some other location, and then we'd have to try and register or align these two 3D point clouds together to fill in the gaps. And you can also see that there are some surfaces that we did see head-on, but for some reason didn't actually get a very good image of. And so, for example, you can see that these windows, right, we get the stone arch around the windows, but we didn't do a very good job getting the window itself. And so I'll talk about that in just a second, too. Another thing that we can do is we can texture this 3D model with the points that come from a kind of co-located color camera. And so here, if I add some color onto this texture, you can see that, now I have something that really resembles the actual building. And, in some sense, you can get away with a lot more. I mean, if you zoom in on it, you can kind of see there are some issues. But like the scan somehow becomes more kind of understandable, more relatable when you've got some sort of 3D texture thrown on top of it. And so later in this class, we'll talk about how do we, take the camera image and align it to the 3D scan if they weren't already kind of co-located in the scanner. So anyway, this is the kind of data that you'll see coming off of 3D scanners. And, it's actually pretty high quality. I mean, if you look at, you can see here that kind of unlike the results that we got from like the structure for motion example, remember we did the reconstruction of the VCC using just the bundle adjustment alone. In that case, you could definitely make out the right angles of the building that we looked at from the top. But if you were to zoom in on those, it wouldn't look super great. I mean, that's not like super highly accurate. Whereas here, the angles and so on that you can get from a LiDAR scan are really very accurate. So I mean, here you get the exact right angles and stuff that really exist in the scene. Okay, so I'm going to move off of this because I think it's making my computer chug along. So kind of what are some of the issues with LiDAR scanning? So again, here's the picture I showed you earlier of fundamentally what we're doing is we're pinging the scene with a bunch of theta comma phi positions. And the scanner does that by basically rotating a mirror inside the top of the scanner and also rotating kind of around its base like this. And so you can kind of say, okay, I want to get this solid angle of the scene, and I want to get it within this within every centimeter spacing on the surface, and then you just let it spin around and it does its thing. And so, like I said, here's a still example. Again, here you can really see the shadows, right? So there's a shadow from this tree. There's a shadow from this solar array that used to be in front of the VCC. And then even here, there's a kind of a vestibule that casts a shadow on the building from this side. And so we'll talk a little about how could we fill in some of those shadows using like a 3D version of in-painting, basically. And here's an example of what the points look like and what the mesh looks like after you connect them up. And this is the picture of if you take the registered color image, you can turn it into a color image like we saw earlier. So here are some of the problems that you can get with LiDAR scanning. So one thing is that obviously you can't, you can't get 3D points on any surface that you didn't see with the naked eye, right, from the perspective of the scanner. And so, for example, if I've got a column in front of, between the LiDAR scanner and the building, well then I'm only going to get the front surface of this column. I'm not going to see the back of the column, obviously, and I'm not going to see anything that the column occluded from the perspective of the scanner. And unfortunately, these shadows kind of spread the further away the object is, right? So if you've got some sort of faraway object, you get these really big shadows on the scene. One thing that you see a lot, and so this happened when we were scanning the MPAC building many years ago, was that, in some sense what you'd like to get is, the physical surface of the building that you're scanning, right? The problem is that when you have something like glass, the laser goes right through the glass and hits the object inside the building and comes back through the glass without getting, refracted. And so the problem is that, when we scan the MPAC building, we basically got the big wooden ball inside the building, but we didn't get the front surface of the building hardly at all, right? So if you're really trying to scan something that's glass, you're going to have a problem. And finally, what happens sometimes is that if you have a object that is just, if this is the laser ray and this is the surface of the object, what you're doing is you're relying on the physical surface to return some laser intensity back to you, right? And so that works the best when the surface is oriented directly perpendicular to the laser ray, and when also that surface is, like, for example, you can imagine that like a matte white surface is almost the best case scenario where that surface just returns a lot of that laser intensity right back to you. If you've got a surface that is almost parallel to the laser ray, it's very likely that most of the laser intensity is going to get reflected off of that surface somewhere out into the world. That's never going to come back to you from the, back to the scanner location. So sometimes you may miss, surfaces that are really parallel to laser rays due to the so-called grazing angle effect. And so, it's not a perfect science. There are also a bunch of other little issues, like, for example, you could argue that the further away the object is, the more that laser spot will expand. And so there are some errors that have to do with distance, although for the most part when you're scanning, I don't think you have to worry about the distance error too much, because what you get back, I think, has fairly uniform errors. And also, there are some minor interactions between the color of the laser and the color of the object, right? So, for example, if I have a red laser and then I hit a green object, well, then that green object may not reflect a lot of that red light back to my camera, whereas a white object might do better, right? So, you can also analyze the kind of intensity of the return of the return. The intensity of the return light gives you kind of a clue about how well do you scan that object. In addition to how far away it is, you can kind of tell how much light came back to me to make the decision. And so the best case scenario is you're scanning objects that are roughly perpendicular to your view angle, and those objects are kind of like light-colored matte objects is the best case scenario. So scanning stuff like a light brick building is really not so bad. But that being said, if you wanted to scan like, and I'll show you some pictures in a second, if you wanted to scan like a beautiful new car, right? Black shiny car just came off the lot, that would really be problematic because, again, that surface is going to, number one, absorb light, and number two, act like a mirror. And so maybe you'll get responses from the surfaces that are really perpendicular to the laser ray, but other surfaces are just going to bounce right off and never come back to the scanner. And so typically what they do in a visual effects scenario is that they will try to powder up, for example, these shiny objects. And so I remember someone telling me a story of one of the cars, I think, for like in Transformers, right? They have all these, super, those cars are never dirty, right? They're like these beautiful, shiny concept cars, right? And so the first thing that the laser scanning guys want to do is to scan this car, and what they may want to do is they may want to like kick some dirt up on it, or even worse, like spray it with some sort of like white cornstarchy stuff to give it this matte white thing. So you can imagine that the, the people who deliver this $80,000 concept car, not enthusiastic about you spraying it with some sort of white, matte cornstarch thing to get it scanned. So sometimes there's like a tension between what you can do on the set and then having to clean it up later on. Okay, so let's talk a little bit about the theory behind how these systems work. Okay, so there's kind of two fundamental ways of doing LiDAR scanning. One way is what's called pulse-based LiDAR. Okay, so what you do is you send a small pulse of light, kind of turn the laser on very briefly. That pulse goes out, hits the world, and comes back to my scanner. And so what you obtain is something like this. So there's basically a very simple equation that says pulse-based LiDAR. So, I have my scanner, I have my object, I send my laser pulse out, it bounces off this object and comes back to the scanner, right? And so the thing I want to figure out is this distance d, right? And so it's a very simple equation, right? Because I'm shooting a pulse of light out, what I can say is, okay, this light, and I measure the time that it took this light to come back to the scanner. So it's like saying, okay, I have a pulse that traveled a distance of 2d. It took me t units of time, and this is what we call the time of flight of the pulse. And what do we know the velocity? So this is the velocity, right? It took me t time units to go 2d distance units, and that velocity is the speed of light, right? Because I know that I'm shooting a pulse of light. So I know this, I measured that, and I want to infer d. And so that means that I can take d is equal to 1/2 ct, is like the key idea behind time of flight scanning. And so, really, what's that? Oh, question?
Yeah, so that's, even for like fairly large distances, that's not much time. So I guess the
No.
question I have is,
Yes, you have to have
how do you even remote, like, so
Right.
all we have is like a little bit of software programmer, and that's pretty fast, but how do you time this properly?
Yes, it's got to be, the timing is extremely precise, right? So if you go back and figure out, okay, so if I want to measure surfaces to within like 5 millimeter accuracy, for example, if you do the computation, that corresponds to, I think it's in the book here, yes, 33 picoseconds. So this is like sensing, timing accuracy. Right, so the receiver electronics on these systems have to be extremely accurate, right, for sure. And so that's why these systems, these pulse-based systems, are generally pretty expensive. So like, we have a LiDAR scanner, a pulse-based LiDAR scanner on campus that we bought, boy, it was a long time ago, maybe like 8 years ago. And I think at the time, with the educational discount, it was like close to $200,000. And I think that probably the professional version of that would have been, maybe double that, right? Now things may be cheaper now, but fundamentally that's what we're talking about. And so the same thing, those Velodyne scanners are also pulse-based, and so those are not cheap scanners either. It's like you just buy one for your, hobby. You have to actually shell out some serious cash to put that together. And so, yes, definitely true that you need to have a very high accuracy receiver. And the other thing is that, not only does it have to be good in terms of distinguishing the time difference between when the pulse is shot out and when the pulse is returned, but, the returned light intensity may be much, much smaller than the sent out light intensity. And so consequently, the sensor has to be extremely sensitive in terms of photons as well as in terms of timing. So these are really high precision systems. So the other thing to say, though, in some sense, you do get to improve things a little bit. You can mitigate any noise in the system by sending out multiple pulses and averaging the distances that you get. So for example, if the scene is stationary and the scanner is stationary, you could send out, say, 10 pulses to the same location and then measure those 10 distances and take the average. And we know that when you take the average of these measurements, the variance of the measurements goes down, right? And so in some sense, you can kind of, if you're willing to wait a little bit longer to scan, you can get more precise scanning by hitting the same scene multiple times. And so I'm not sure that when I don't remember in our scanning system whether we have the ability to trade off the number of pulses. I mean, some very advanced systems may let you make those little very under the hood decisions. But all that being said, the resolution of these sensors in terms of the difference between the distance of the surface you get and the distance it actually is really is like millimeter accuracy, even if you are tens of meters away from a surface. So it's really impressive to scan something and get like this very nice high quality, reading. But that being said, not everybody can afford to buy a pulse-based system, and not everyone can afford to wait for the pulse-based system to give you, the results as it kind of chugs through the scene. So there is a faster method called phase-based LiDAR. Okay, so the idea behind phase-based LiDAR is the following. So phase-based LiDAR, let me show you a picture first. The idea behind phase-based LiDAR is a little bit different. So instead of sending out a kind of a, pulse, we have a continuously on laser beam. Okay, so it's basically continuously being modulated. So for those of you that have taken signals and systems, hopefully some of you have taken signals and systems, we talked about amplitude modulation. So what you're doing here is you're basically saying, okay, I have a sine wave. So the sine wave has a very high frequency, right? This is the frequency of the light. But what you do is you kind of shape the envelope of the sine wave with a much lower frequency wave. So this is called the carrier frequency, and the modulation frequency basically turns that into something like, you say, okay, here's my, slowly varying envelope. And instead, I modulate this high frequency thing inside this envelope. So it's still wiggling very fast, but the amplitude of the wave is changing much more slowly compared to the frequency of the carrier wave. Okay, and so how does this help us? Well, the idea is, okay, so what I do is I imagine that I, again, have my sensor and I have my object, and I'm sending out, in some sense, you imagine that you're kind of like sending out some portion of a slowly moving sine wave, right? That hits the surface and it comes back to me. And what I do is I measure the difference in the phase of the thing that I receive, right? So that kind of tells me at what point in the cycle am I when the laser came back to my sensor, right? When the measurement came back to my sensor. And so if the surface is not too far away, then the phase delay is small because there hasn't been that much time for this slow frequency sine wave to change that much when it comes back to me. Whereas if the surface is far away, then maybe I'm all the way almost back to my original, zero starting position. And so here, what I look at is what we call psi, which is called the phase shift. The phase shift of the modulated signal. And so what I have is I have the if omega is the frequency of the modulated signal, you can show that the time of flight is related to these two things by the following, where I have the phase shift, the frequency, and the time. Okay? And so then if I put that together with my previous equation, I can obtain that the distance to the surface is, again, I have C like this. If I kind of combine my previous two equations, so this is saying I know the frequency of the slow sinusoid, I know the phase shift of that sinusoid, I know the speed of light, and so this turns out to be, quite a bit faster than the pulse-based method, because the laser is always on. It's not sending out pulses and waiting for them to come back. The laser is always just modulating this wave of light. And so fundamentally, I can get a whole bunch of continuous measurements coming back from a given point in the scene. I can just kind of stare at that thing, watch my sinusoid as it comes back for a few seconds, not a few seconds, a few fractions of a second. Then I move to the next point and I see the same thing, right? So instead of getting a bunch of discrete measurements, in some sense you're getting a whole bunch of continuous measurements of this offset phase, and that can be, a lot faster. And so when you're on a busy movie set, you may want to use a phase-based scanner instead of a pulse-based scanner. Okay. The downside is that, there is an ambiguity here, which says that, suppose that I've got an object that happens to be kind of exactly one period away, or maybe like half a period away from the scanner. So when I come back to the scanner, I've gotten one full period, right? But now if I have another object that is one full period away, I've gone one full period here and I've got one full period back, so the phase shift for both of those things will be exactly the same. And so basically you have this kind of problem where you can't distinguish things that are, well, so there's an ambiguity. If you restrict yourself to say, let me say here, there's kind of a maximum unambiguous sensing range. I mean, you could imagine some sort of computer vision techniques, or not computer vision techniques, signal processing techniques that could kind of get around this issue. So, for example, if you've ever done any sort of microscopy imaging, you may have heard of phase unwrapping. That's kind of a similar problem from another biomedical imaging problem where basically you can only see the phase, but you really need to unwrap it into, you kind of like to know, okay, well, this was not actually, 3 pi over 2 phase shift. It was actually 3 pi over 2 plus 2 pi or plus 4 pi. So you kind of want to know how many 2 pi's are you off from the return. But that being said, I think that in most, kind of physical sensing situations in practice, you basically say, okay, I'm going to say, I know that my sensor is going to be unambiguous within a certain range. And that range could be something like, 60 or 80 meters. I mean, it's not like it's, 5 feet away. So typically in most real-world scenarios, you're not up against this ambiguity with the kinds of environments that you're scanning with phase-based LiDAR. So in general, you don't really have usually a problem with this. So I think that, again, if we were to do it all over again, we would probably buy a phase-based scanner, not only for price, but also for, time. Because right now, our old scanner, it takes a long time to scan stuff. And so, like we talked about, no one on a movie set has any interest in the visual effects guy sitting around while something chugs around the scene and there are no actors present doing acting, right? So, I mean, you want to be able to get in and get out with your scanner as quickly as possible. And so I'll talk about this a little more detail next time, but I mean, I had a great visit to a place called Gentle Giant Studios in LA that basically does all sorts of types of scanning. They scan movie sets, they scan actors, they scan props. I'll show some examples of that in just a second. And so, they have some good stories about, the way it used to be, that apparently the laser scanner used to be like the size of a washing machine. It would take forever, and now it's like this little thing just sits on a tripod, and you can set a whole bunch of them up, let them all kind of go at the same time to get these quick scans. And maybe you have a master pulse-based scan that's going a little bit slower that, is not in anyone's way. And so let me just see here of what I've got in my presentation. Right, so this is the kind of example that you'd have in a visual effects scenario. So what you do is you take one of these LiDAR scanners, you plop it down on the scene, and then you would acquire distances to points. And so here what you've got is basically the scanning company has already helpfully classified these 3D points into different classes, right? So gray is building, purple is tree, green is bush, yellow is sidewalk. And so basically this helps the visual effects people later on in the pipeline understand, okay, well, I really only need to look at these points for my algorithms. Now, that being said, some of this may be automatic and some of this may be extremely manual to kind of automatically segment out. Because again, if all you've got is the literal 3D return, it's very difficult. We'll talk a little about 3D feature extraction, right? So in 2D, things like SIFT features and so on are very easy to extract. You can use those as the basis for telling what different objects are. But in 3D, you looked at that cloud of angry bees, right? It would be very difficult to say, okay, this clump of points is a building and this clump of points is a bush, right? That's kind of tricky to do. So anyway, this is the set from, one of the sets from X-Men First Class, the one where the mutants are getting broken out of this building, the young mutants getting broken out. This is an example of a scan from Battle Los Angeles, quality movie. And so here you can kind of see, I think that what you're seeing here, these circles on the ground, are probably the places where the laser scanner was actually put. And it rotates, 360, or rotates in 360 degrees. And so you don't get data like right in the middle of where that scanner is sitting. Here's another view of that environment. So you can see this is a very large freeway set where they've got, maybe 25 cars. There's a helicopter here that's crashed. So you get a sense of the scale of this scan is very large. And they've done this by sticking together multiple scans from different perspectives. And so we'll talk about how that works next week. So here, this is a scan of the set from Thor. And so when they did Thor, so most of the, these days, there's lots of green screen on sets and so on. But for Thor, they actually built this kind of 2-block square town in the middle of the New Mexico desert, I think, and filmed on this real set. And so they scanned that set very thoroughly, right? And so again, you can see that these circles are basically the centers of where they place their scanner, and this has been a registration of all those points into one coordinate frame. And so here you can see there's one of those diner from Thor. And this is the kind of level of quality that you get. And so, you have you got a whole bunch of points. And so again, if you now wanted to take the if you wanted to destroy this building, right, when the Guardian thing comes out and blows buildings away, so now you've got very accurate 3D structure of things that you can use, for example, to blow up the building and say, okay, now what if this 3D surface was made out of concrete and I apply a physical simulation to blowing something up, right? You can also do laser scanning for objects. And so here are some cars from Fast 5 where basically, again, to get these car scans probably required some sort of like cornstarching of the cars to get really nice shapes, because you can probably see that these are shiny objects. Also, that being said, because these have clearly been kind of post-processed, again, into, like they've segmented out this red thing, they've segmented out the wheels. And so it's definitely highly possible that some artists have gone in and touched up the points that weren't visible by the scanner. Maybe they connected some surfaces. Here's another example of a car. And again, you can see that this is not just a model because of, for example, there's this big dent on the door frame, right? And so maybe for visual effects realism, they actually smashed this car up on set, but now they want to further smash it up in the digital world, and so they need to make sure that there's a smooth transition between the actual car and the physical scene and the 3D version of that. Another car. This is there was a train in Fast 5, right, where they drove the cars off the train. This is the safe that they were dragging around on the street, right? So basically, if you've got like a kind of a large object, right, like probably something that is car-sized or building-sized, then you want to use a LiDAR kind of system. I mean, that's the right kind of system to use. We'll talk next time about structured light scanning, which is more like if you're trying to scan a person-sized object or a prop-sized object. And so again, going back to the self-driving cars, this is the kind of thing that you see from a Velodyne scanner, where you've got a car-mounted LiDAR scanner that is on the top of the car, and it's basically swinging around in a circle and acquiring rings of data. And then you can imagine that the Google cars are, automatically saying, okay, this is a car, this is a pedestrian, this is a road sign, and so on. And of course, those cars also have all sorts of cameras and inertial sensors and stuff like that. Now, we haven't talked about, we'll talk about that maybe a little bit next week, the car is moving, obviously, while the thing is scanning. And so somehow you have to know how to put all these points together into the right coordinate frame. So you have to have actually, number one, you have to have fairly accurate inertial measurements of how the car is going. You probably also have to have cameras to help you register where the car is now to where it was then. That helps you kind of align the 3D points also. Okay, so that's kind of it for LiDAR. Any questions about that process? I would have brought my LiDAR scanner in, but it's heavy and cranky, and you just kind of look at it. But right now, I think it's sitting over an MPAC. They've been using it to scan concert halls and stuff like that. So again, there's an example of there are lots of reasons to apply LiDAR other than visual effects, right? So they use LiDAR a lot in archaeological preservation, right? So for example, they'll go to Pompeii and scan the ruins, and of course that was an issue, right? Because I think that just recently there was some sort of an accident, or not accident, but landslide or crumbling at Pompeii where they lost something that had been there for a long time, and they had scanned it, hopefully previously that, so they kind of preserved the cultural heritage with 3D scanning, right? So this is a very common thing to do. Pretty much any architectural or archaeological site that you can imagine has probably been pretty well scanned by 3D scanners by now. And I was saying something else before this. What was I saying about where else to use it? I lost my train of thought. It's a shame. Anyway, so yes. All right, so let's talk a little bit about a different alternative to LiDAR, okay? And so that is what's called a time-of-flight camera, which is a little bit, weird because we just talked about time-of-flight as the principle for LiDAR scanning. So this is kind of like a slangy term, right? So this here is what you'd call a time-of-flight or a flash LiDAR. Sometimes you hear it called flash LiDAR. And so this is a $8,000 cube, or at least it was at the time. And so what this does is it acquires. So one thing about LiDAR that is, disadvantageous is that you have to basically let this scanner percolate through the scene to get the 3D model. Whereas really what you'd like to get is like live 3D scanning. I mean, in some sense, the Velodyne scanner is doing live scanning, but again, that's not a cheap thing. What you'd like to be able to do is get like live, real-time 3D. And of course, that's the kind of thing that is like what the first version of the Microsoft Kinect was doing. We'll talk about how that worked next time. This actually, we're going to show in just a few minutes a demo of the second version of the Microsoft Kinect, which does use what's called a flash LiDAR or a TOF camera. And so the situation with this is that what you see around, or what you have around the border of this silver disk is a set of infrared lights. And so they're basically bathing the scene in front of the camera with basically, I think this is usually phase-based, modulated infrared light. And then there's a whole bunch of sensors in here, but not a lot. I mean, like, compared to a digital camera, these things are generally, I guess prior to the Microsoft Kinect version 2, these things are generally pretty low resolution. So I think this thing is really like it's like a 176 by something image, so much lower resolution than even the crappiest webcam that you might find on the market, right? But the advantage is that it can do the scanning at basically 30 hertz. And so you're trading off the amount of time it takes for you to get a scan with the resolution of the scan. And so definitely there are a lot of cases where what you want to do is get kind of real-time frame rate depth sensing. And so what I say, the third kind of modality, sometimes you hear this called flash LiDAR, and sometimes you hear this called a TOF camera. And so, again, these are usually fast. I would say about 30 hertz frame rates. They're usually, I would say, low resolution. And so, I don't know if I have it in the book here. Yes, this was, this was a SR 4000 sensor from Mesa Imaging. And that was a 176 by 144 image. And then also, I would say it's noisy, right? By which I mean, the measurements are not as accurate, and you also get a lot of kind of, you can see some visible noise. I'll show you an example of that in just a second. But they're very easy to set up. I mean, so basically, you usually just kind of pop it on a tripod, turn it on, and suddenly you're getting like real-time 3D depth. That's pretty cool. And so let me show you, actually, let me just see if there's anything else I want to show you in this thing. Right, so this is the kind of thing that you get. So this is a picture of my students in the lab. This is a real camera image from above the desk, and this is a frame of a time-of-flight-based, or TOF camera-based image. And so here, the wider something is, the further away the object is. And so the floor is furthest away, and you can kind of make out that, the person's back of the chair and their shoulders are kind of gray, and the top of their head gets darker, but then there's a whole bunch of missing stuff. For example, this person has like shiny black hair, and so the time-of-flight camera didn't respond very well to that and just didn't give me any response at all on that region of the image. And so, and also again, if you look at the periphery of the image, the camera response is much noisier as you get out to the edges of the image. And so fundamentally, you don't really get much response in kind of like this outer circle. And so actually, we were using time-of-flight cameras in one of my research projects for detecting occupancy in a smart room. So you guys maybe know about the Smart Lighting Engineering Research Center on campus. So basically, we've tried to instrument these kind of smart rooms on campus to automatically be able to tell, where are the people in the room, and kind of coarsely, what is their pose? Are they standing up? Are they sitting down? And then the idea would be that the room would respond by changing the lighting in the room to kind of match up with what the person was doing, right? So let me just come back to this. So here's an example. This is a new room that we just built up in the CII, where these things in the ceiling, we've got 18 kind of very low resolution time-of-flight sensors, and so that's what these look like. So these are called iris sensors, iris matrix sensors. And again, these are even lower resolution. I mean, these are like literally 25 by 20, pixels, right? So extremely crude. But, one advantage of them is that time-of-flight is a good choice for this application because you don't want to feel like, you could do this very easily with cameras, right? Why don't we just put cameras in the room, right? But the thing is, you don't want to feel like your room is monitoring you with cameras all the time, right? Or even if you trusted that no one was looking at the video, you don't want to feel like someone could use some sort of Heartbleed vulnerability to hack into the cameras and get real-time video of you in your home, right? That would be bad. So the idea behind time-of-flight here is that things are really, really chunky, pixel weighted, but they're good enough to be able to tell who's in the room and roughly are they standing up or sitting down. That's really all we wanted to do for this application. And so, and then you can kind of see here we have these color tunable lights. So these lights may, dim in areas of the room where there are no people or where there's already sunlight coming through to provide lighting in the room, but they may light up over the desks of where people are working, right? And so let me show you an example of that working. Right, so what you're going to see at the top is a mosaic image of all of the time-of-flight sensors put together, and that's the raw output of these time-of-flight sensors. And at the bottom, you're going to see a computer vision algorithm that is basically tracking the people as they move around at 15 times normal speed. So it's not like... Okay, so kind of what you're seeing here is on the top, you see the raw output of the time-of-flight sensors. You can see there's actually a bit of noise in the sensors, right? So for example, here on the table, you can kind of see there's like this kind of wavy pixelated noise. Same here, this is a TV screen that is casting extra light into the scene. So the sensors themselves are pretty noisy, but if you look at the tracking results, they're good enough. I mean, they're good enough to track the various people as they move around the room. And so here, you've got up to 7 people that are standing, sitting around, and so our next phase of research is going to be to use these, real-time person locations to develop control algorithms for the lights in the room. So it's kind of a fun project. And if you're interested, we can go over, or you can stop by the, the smart conference room over at the CI to actually see it working. Okay. So, I guess while I'm on this page, what I would say is that the most notable current use of this is for the Xbox One, Kinect version 2, right? So this version, this Kinect that just came out Christmas time, I guess, uses a real-time time-of-flight camera to extract 3D distances to the scene, and also to do the real-time 3D skeleton that we were talking about kind of in the motion capture chapter. And so, since this just came out, and there isn't a lot of detail on it, I thought we would take our beta kit here that my student Dan is working on kind of putting together, and we'll show some results from it so you can see what it looks like. So why don't we try and do that demo, but I may need your help, Dan. So let me close this up. And, okay, so we don't want to close this up either. Okay. So make this a little bit bigger. Whoa. I think this is just a little bit slow to respond to my commands here. There we go. So what you're seeing here is a live camera feed, and then this is kind of like a crude depth image. But the most interesting thing is this image, right? So let's see what we can see here. So I guess we can see that it's picking up these are the ceiling lights, right? And then who is directly? There's a chair in front of Matt, right? So Matt, wave your arms a little bit. Oh, maybe this is you. Right. So you guys can come in front of the Kinect. Let's see how well it does. There we go. And so actually, this is probably even faster than it looks just because my laptop is kind of pokey. And so if I rotate this to look down from above, right, here you can kind of see again. So actually, this is not, the sweet spot is really, I guess, sorry, I'll just move this over here, right? So let's see how we... So it looks like, we're getting, I don't think we're getting all the way to the back of the room, or at least it's hard to tell whether we're, that's pretty good there. But you guys in the back of the room, like, I don't think we see you guys at all. So, sorry. Oh yeah, there we go. There's somebody, right? And again, this is probably partially because of occlusion, I would guess. So like if you think about what we're seeing from the point of view of the scanner, it may be something like this, right? So I mean, if you think about it from the desktop view, we do see about as much as you as we could. So if anyone wants to move down to the aisle, or if you guys are still out, you guys are too shy. Yeah. So again, I think that it's actually probably a lot better than this in terms of frame rate. But you actually get, so one thing that's surprising about this is that this is actually a much denser time of flight image than I was expecting. Do you know, Dan, what the resolution of this is? Although I guess actually you could figure it out from looking at the, I guess we don't know what the resolution of this image is. So this is basically the real time, oh, I guess I can't make this bigger. So we can't make this axis bigger, I guess? Or we could also do the Kinect, what do you call it, the Kinect status, right? But we have to stop the service. All right, we'll come back to that in just a second. So what the other demo is the skeleton, right? So if I do display body data, oh yeah, so that's a better image up there. So like this is basically the real-time depth image kind of colored, where I guess the blue is closer and red is further away. And then I guess there's no one in the field of view of the Kinect, so we have to have my lovely volunteer stand in front of this and see. So when you move into this, you think it's going to pick up your body?
Sure.
No go. You think it's maybe the coordinates or something?
Yeah, I don't really know what's going on with stuff.
Maybe if we were to point it like a different direction, like a little less clutter in the background.
Maybe.
Skeleton fail. Well,
Try running it again before you move it, because sometimes the Kinect calibrates.
let's try this again here.
You might also just try to restart the Kinect itself.
Yeah, you think that if we restarted this, it would be better, Dan? Like just restart the service?
Yeah, try it.
Okay. So should I restart MATLAB also?
Yeah, you probably need to.
All right.
For some reason, it goes out.
Okay. So then I need to stop all the services, right?
We'll press enter. So this is
All right. And this one we also have to stop?
I should.
Okay. Although if we just stop this and look at the Kinect, yeah. So let's just stop with this. Fail. Oops. So Kinect status, right? So here again, you can kind of see, like this is the real, so actually you can already see that what Dan was showing was kind of cleaned up. So again, you can see this kind of characteristic noise around the edges of the time of flight image, right? So this is, again, definitely not as high quality of a depth image as you would get from a LiDAR sensor. But, for the purposes of consumer, real-time game control, this is perfectly good, right? Even around, it's kind of hard to tell. You probably can't see it just because of the way that this is colored, but there's probably, a lot of noise that you can't see because of this color map happening too. And so, all right, so if we cancel out of this, and then we restart the Kinect service, which I have to do from here, right? Kinect service, right? Okay. And then MATLAB.
You need to run the service, run my service again.
I need to run your service again.
It should be in the folder. Just up in the
Yep.
MATLAB,
Yep.
and then bin x64.
Debug.
And we talked about
Alpha
execute.
source. Okay. So then I should probably
Then back to MATLAB.
back to MATLAB. I have a feeling that MATLAB is, all right, here we go.
It's taking a lot of resources.
Yeah. Well, I guess now I can unplug the hover cam. Okay. So, what? All right.
Back to that.
Yeah, I think maybe the easiest thing to do is just to go.
It should be in the history on the right.
Yeah, you're probably right. Okay, so where do I want to be? Is this
V2 display.
YouTube display? Okay. Apologize for the people at home who are watching us slog through this demo. So, I mean, this is a beta SDK where fundamentally there's not a kind of academic Kinect interface that's been kind of generally approved yet. Did I just run this? There we go. Hey, here we go. Okay, so let's zoom in on this a little bit.
Too tall for it? No, I just don't know it.
It's weird because it's just.
It's kind of a stubby head.
There you go. You got a head now.
Oh, don't go too far.
There we go.
That's pretty good.
Yeah, this is one model that I drew.
Right, so Dan put this together, and so basically, so when the frame drops out, is that when it's lost track?
Yeah, it's still really buggy. Like sometimes it just drops a frame and it's not making figure out the whole.
And so you can see, unlike the old Kinect, this one has. I don't know whether we can see the grasping of the fingers. Like, is that? You know, one thing that Oh, I see. Is this ball your thumb? Is that the idea?
Yeah, there's I got a thumb and a tip of my finger.
Right.
I didn't have that before.
Right. So it used to be that the Kinect didn't do very well. So again, I don't know whether or not the underlying. I mean, I'm sure that when they made the version 2 of the Kinect, they totally changed they totally revised the skeleton estimation too. I assume this is again the result of some crazy, weeks-long trained decision tree classifier that's very fast to apply. But I don't know whether there's any temporal coherence here. I mean, you can still see there's a little bit of a, temporal wiggle. I mean, the body seems pretty firmly planted. I guess that the hands seem like they're kind of jiggly a little bit. Yeah. But again, you think about what you could really reasonably infer from, looking at a depth image of a person. I think it's already asking a lot to be able to even estimate what their wrists are doing and what their fingers are doing. So that's pretty impressive, I think. So will it work with somebody else in the frame, or is it only one person?
I don't have it for one.
Oh, okay. Too bad.
If you move your arm behind your back.
Yeah, try some weird
So
poses.
if I put my hand towards it, so usually my hand will include my wrist.
Uh-oh.
Right there, you can see when it turns yellow, that means it doesn't have a very good estimate.
So yellow means bad estimate. Okay. So what if you were like cross your hands in front of your body? No, that's okay. What if you put one hand behind your back? Ah, see, yeah.
It's still getting like a pretty decent estimate for my hands.
Yeah. So does it work when you're sitting down? It looks like it's kind of. See, now it's a lot. Oh, sorry, I'm trying to wriggle this around here. How do you do? Oh, the hand, right? Yeah. Right. So this is the side view of you sitting down. So again, it's probably trained more or less on expected poses as opposed to. Oops, sorry, I'm flying around you here. I thought it was on the hand here. Yeah. Well, that's pretty neat, right? So, okay, so that's the, kind of latest and greatest TOF camera-based technology. I think that probably, there goes our crazy avatar. All right. So I think that's about it for today. Any questions about either LiDAR or TOF cameras? Okay, so let me stop my recording, if I can. Goodbye, little stick figure man.